Hi, thanks for joining me today. I've got a non-standard proof I want to show you. You guys like the non-standard proofs, as do I, but this one is really non-standard, and I think you're going to love this one. So we want to solve the Basel problem, which basically means we want to evaluate this infinite sum here, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. But I'm going to be evaluating it using probability. Now, this is something I'd never heard of before I saw this, evaluating an infinite sum using probability. Okay, so that's what I'm going to be doing, and without much further ado, let's get stuck in. Okay, so the way we're going to start this off is by introducing two random variables, x1 and x2. Now first, if you haven't heard of random variables, don't worry too much. It's essentially something you can assign a probability to or a probability density to. But for the purposes of this video, as long as you have just a vague understanding of what they are, that will do. Okay, so x1 and x2, and I say that they're IID random variables, which simply means that firstly they're independent from one another, and also they're identically distributed. So they have the same distribution, and that's this distribution here. The probability density, P of x, and this has this for x negative is 0, and for x non-negative it's just 2 over pi times 1 over 1 plus x squared. So let's quickly check that this indeed is a probability density function, which means we have to check that it's non-negative. Well, that's very clear just from this. It's either 0 or it's 2 over pi times 1 over 1 plus x squared, and because x is real, this guy is going to be non-negative, and as is this thing here. So multiplying two non-negative quantities is certainly going to give you a non-negative quantity. And the last thing we need to do is just check that the integral of p of x dx from negative infinity to infinity is 1. And that's not too difficult to see. The integral from negative infinity to infinity of p of x dx, that's just equal to, well, we don't really need to worry about x negative because it's 0 there. So it's just the integral from 0 to infinity of p of x dx, which is this guy here. But I can take the 2 over pi out to the front, and then it's just 1 over 1 plus x squared dx, and this just has a nice antiderivative, namely inverse tangent x. So this is 2 over pi times inverse tangent x. That's from infinity to 0. When you plug in infinity into inverse tangent x, you get pi over 2, and when you plug in 0, you get 0. So this is just 2 over pi times pi over 2 minus 0, and that of course is 1. Okay, so p of x certainly is a probability density. Now what we want to do is introduce a new random variable y, and y is, let me just write it here, is just going to be x1 divided by x2. But I'll write this up on a clean whiteboard, so let me just clean up the whiteboard and we'll continue. Okay, so like I said, we've introduced this new random variable y, which is just x1 divided by x2, and what we want to do is work out the probability density function for y now. And to do that, firstly what I'm going to do is just consider the general probability that y lies between a and b. For a and b, just some non-negative numbers. Okay, well let's just write this thing here as a probability that a is less than or equal to x1 over x2. Okay, and then that thing that has to be less than or equal to b. Then of course we can just multiply this inequality through by x2. So this is equal to the probability that ax2 is less than or equal to x1, which is less than or equal to b x2. And now what I'm going to do is just write this as a double integral. Let me just write down what the integral is, and then I'll explain where each of the terms are coming from. So this is the integral from 0 to infinity of au bu of p of x1 x2 of x1 x2 dx1 dx2. Okay, so this is what our integral is. So it's the integral from 0 to infinity of the integral from ax2 to bx2 of this thing here, which is the joint probability density of x1 and x2, so the random variables x1 x2, of dx1 dx2. Why is this the case? Well, if we look at this firstly, this inner integral, so we're looking at the x1, that clearly takes values between ax2 and bx2, hence those limits there. But of course x2 can be any value from 0 to infinity, and hence why we have this 0 to infinity thing here. And this px1 x2 is just a probability density, so this thing here, which is what we're trying to work out. And that's why this line is equal to this integral here, this double integral. But by independent of x1 and x2, we can write the probability density of the joint probability density is just the individual probability densities multiplied together. So this is just px1 times px2 dx1 dx2. Now what I'm going to do is just a simple u substitution to get to make this inner integral, just make the limits a and b as opposed to ax2 and bx2. So to do that, I'm just going to say let xi equal x1 over x2. Then that implies that d xi is equal to 1 over x2 dx1. Okay, so if I just plug that back into this thing here, this integral, the outer integral stays the same. It's the integral from 0 to infinity. And then this inner integral, so when x1 is equal to ax2, we have that xi is equal to ax2 over x2, which is just a. And when x1 is equal to bx2, then we have that xi is equal to bx2 over x2, which is just b. So it's the integral from a to b now. Px1 is now p. If we multiply this thing here by x2 on both sides, we get that x1 is equal to x2 psi1. Sorry, just x2 psi. So x1 is equal to x2 psi, and then px2 just stays the same. And then dx1 now is just x2 d psi. And then of course we've just got our dx2 there. Okay, so our inner integral now is from a to b and it involves some different terms, and our outer integral stays exactly the same. What I want to do next is just switch the order of integration, and that to sort of justify requires Fubini's theorem, which I'm not going to go into too much detail, but it's basically because this thing here, the thing we're integrating, converges sufficiently quickly, so we can just swap the order of integration. And just to recall that this thing here, remember, is 1 over 1 plus x squared times the constant 2 over pi. So this guy here is going to be of order x2 squared. This thing here is going to be of order x2 squared, and then 1 over x2 squared. This is going to be of order 1 over x2 squared, and that's going to be of order x2. So combining them, that's going to be of order 1 over x2 cubed. So that's going to converge sufficiently nicely. So we don't have to worry too much about that. And it's also going to be of order 1 over xi squared. So it's converging very, very nicely. So we're going to swap the order of integration. So it's now the integral from a to b of the integral from 0 to infinity of this guy here, and then of course we've got to change these guys. So dx2 first, and then d psi. Okay, what I want to do now is from this derive the probability density function for y, but to do that let me clean up the whiteboard and then we can continue. Okay, so we've showed that the probability that y lies between a and b is given by this double integral here. And now this is just for general non-negative a and b. So what I'm going to do is look at the particular case when a is 0. So I'm going to swap this a out for 0. And when b is just x, so some variable x, not a random variable, just a regular variable, little x. Okay, so the probability that y lies between 0 and x. Now we actually know that y is a non-negative random variable because remember it's just x1 over x2, and x1 and x2 are also both non-negative. So when you divide one by the other, you're going to get something non-negative. And I guess one small thing to point out is you might worry, well, what if x2 is 0? But the probability x2 is 0 is exactly 0. Because remember, it's a continuous random variable, so the probability that it equals a particular exact value is just 0. So we don't have to worry about dividing by 0. So in fact, y is a strictly positive random variable. And yeah, with random variables, continuous random variables, generally you can be quite loose with the inequalities. You don't really care if it's strictly less than or less than or equal to. But that's just a small aside. So we have the probability that y lies between 0 and x is given by this double integral here. And then what we want to do is just differentiate both sides, because we know this guy here is just the cumulative density function for y. So when you take its derivative, you're going to get the probability density function for y. So that we have that p y of x, so the probability density for y, is just the derivative of this guy with respect to x. And we can just use the fundamental theorem of calculus. If we think of this guy here, this inner integral, as some function of xi, which it is, then we've got the integral from 0 to x of f of xi d xi. So when we differentiate that, we're going to get f of x. So yeah, when we differentiate that with respect to x, we're just going to get f of x, which is just this inner integral here. When we plug in xi equals x. So the integral from 0 to infinity of p of x times x2, p of x2, x2 dx2. Okay, and just so we don't get confused between x's and x2's, I'm just going to swap all the x2's for u's for now. Okay, and of course that's fine because x2 is just a dummy variable here. Like so. Okay, so the probability density function for y is equal to the integral from 0 to infinity of this guy here, p of x times u times p of u times u du. Okay, now what we want to do is sort of write this as a more explicit integral, because remember we know what p is. It's just 2 over pi times 1 over 1 plus u squared. So we can write this thing here as the integral from 0 to infinity of p of xu, which is just 2 over pi times 1 over 1 plus xu squared, times 2 over pi times 1 over 1 plus u squared times u du. Okay, but of course we can just take out the constants, which is 2 over pi and 2 over pi, which gives me a 4 over pi squared out the front. This is equal to 4 over pi squared times this integral here, the integral from 0 to infinity of 1 over 1 plus x squared u squared times 1 over 1 plus u squared times u du. Okay, now what I want to do is compute this integral, but again, we've run out of space, so let me bring this to the top of the whiteboard and we'll continue. Okay, so I've just shown that the probability density of y is given by 4 over pi squared times this integral here. Now, if you've seen the Basel problem before, or you know what the sum equals, you know that there's a pi squared involved, and we've got a pi squared here. So we're sort of, we know that we're along the right tracks. Okay, so what I want to do now is evaluate this integral here, but this is kind of a boring, laborious integral. You just do it by parts. There's nothing too interesting there. So I'm just going to write down the antiderivative, and if you don't believe me, you can just check that my antiderivative is true just by differentiating it with respect to u and making sure you get this guy here. So I claim that this thing here is equal to 4 over pi squared times 1 over 2 x squared minus 1 times log 1 plus x squared u squared divided by 1 plus u squared. Okay, and that's from u equals infinity and u equals 0. Okay, so if you differentiate this thing here in the square brackets with respect to u, you get this thing here. Okay, and I'll just leave that as a little exercise to you. Now, because we're sort of integrating with respect to u, this thing here is a constant, so we can just bring it outside the square brackets, like so. Okay, and we want to plug in u equals infinity and then u equals 0. Well, let's just look at u equals 0. We're going to get log of 1 over 1, which is just log 1, which is just 0. So we're doing something minus 0, so we don't really need to worry about the lower limit. We only need to worry about the top limit when u equals infinity. But we actually have to take u approaching infinity, because clearly we're going to get a log of infinity over infinity situation. So let's work out the limit as u goes to infinity, too lazy, of this guy here. So this is 1 plus x squared u squared over 1 plus u squared. As I say, it's infinity over infinity, so we can use L'Hopital's rule and just differentiate the top and the bottom. This is just the limit as u goes to infinity of the derivative of the top with respect to u, which is just 2u x squared, divided by the derivative of the bottom with respect to u, which is just 2u, and of course the 2u's cancel, so we're just left with x squared, and of course that's independent of u, so this guy here just equals x squared. Okay, and of course we can bring the limit as u goes to infinity inside the logarithm, because the logarithm is a continuous function. So all in all, this guy here just equals 4 over pi squared times log of x squared divided by 2 x squared minus 1. Okay, this log x squared, well, we can bring this 2 out the front here, but that cancels nicely with that 2. So all in all, we're just left with 4 log x divided by pi squared times x squared minus 1. Okay, so the probability density function for y is given by this thing here, and this is when x is positive. Okay, now what we want to do is look at where the probability that y lies between 0 and 1, which we're going to evaluate by integrating this probability density, but then we're also going to just have a stare at what y is, and hopefully the probability density, hopefully the probability that y lies between 0 and 1 is quite obvious, and then we can compare two expressions, and then from that we will get one step closer to solving the Basel problem. Okay, so we've shown that the probability density of y is given by this thing here, so pyx is equal to 4 log x over pi squared times x squared minus 1. What we want to do now is work out the probability that y lies between 0 and 1. So the probability that we have y being between 0 and 1, this guy here is just the integral of the density between 0 and 1. And the density function is just this thing here. So let's strip out the constant, 4 over pi squared times log x, all over x squared minus 1 dx. Okay, but of course, because x is between 0 and 1, log x is going to be negative, and x squared minus 1 is also going to be negative. So what I want to do is just introduce a minus sign just to make things look a bit nicer. So this is equal to minus 4 over pi squared times the integral from 0 to 1 of log x now divided by 1 minus x squared. So I've just swapped the 1 and minus x squared, which introduces the minus sign, which I brought to the front there. Okay, dx of course. But now we can notice that this thing here, 1 over 1 minus x squared, we can write using our geometric series formula as an infinite series. So this is just minus 4 over pi squared times the integral from 0 to 1 of the sum from n equals 0 to infinity of log x times, times x squared to the n dx. Okay, so where does that come from? So the log x, we can sort of bring out this summation, it doesn't really matter, but we have 1 over 1 minus x squared, so that's a sum from n equals 0 to infinity of x squared to the n, and of course we can actually just write this as x to the 2n dx. Okay, and now what I want to do is just swap the order of summation and integration, and again that requires Fubini's theorem, but I'm not going to go into that into too much detail, but it's basically because this thing here converges sufficiently nicely, and you can kind of see that it does because this thing here, x is between 0 and 1, and log is x is a lot stronger than log x, so this thing here won't be able to grow very nicely because obviously this doesn't behave too well near x equals 0, but this thing behaves well enough to ensure that this guy doesn't do any harm near x equals 0. But of course, you've got to justify that rigorously, but I'm not going to do that in too much detail. I'm just going to swap the order of summation and integration, but if you know Fubini's theorem, check that you are indeed allowed to. Okay, so I'm just going to swap these guys here. So this is a sum from n equals 0 to infinity of the integral from 0 to 1 of this guy here. Now this thing here looks quite tough to integrate, but because we know that n is a natural number, there's a little trick we can do to evaluate this integral here, which is what I'm going to do once I clean the whiteboard. Okay, so we have the probability that y which lies between 0 and 1 is minus 4 pi squared of the summation of this integral. But we want to evaluate this integral here, and I'm going to show you how you can do it using a quick trick. So what we're going to do is call Im to be the integral from 0 to 1 of x to the m times log x dx, and m is just greater than or equal to 0, but a non-negative integer. So perhaps just to make that explicitly clear, m is a natural number or 0. So a positive integer or 0. Okay, and this thing here, what we're going to do is just use integration by parts to derive a recurrence relation. Okay, so we're going to have let u be equal to log x, and that means that du is equal to 1 over x dx, and we're going to have dv being equal to x to the m dx, which implies that v is equal to 1 over m plus 1 x to the m plus 1. Okay, so that's just integration by parts. Let's just use the formula. So that implies that the integral we're trying to work out, Im, is equal to the integral from, uv from 0 to 1. So that's log x over m plus 1 times x to the m plus 1 from 1 to 0 minus the integral of v du. So minus 1 over m plus 1 times this guy here. So 1 over m plus 1 times the integral from 0 to 1 of x to the m dx, because obviously x to the m plus 1 divided by x gives me x to the m. Okay, now this thing here, when we plug in x equals 1, well, we just get log of 1, which is 0 times 1 divided by m plus 1, so that's just 0 times 1 divided by m plus 1, which is 0. Now when we plug in x equals 0, we get some difficulties with log x, but remember we're just taking the limit as x goes to 0 plus of this guy here, and this x thing here is very strong. It's going to be stronger than this log x, and this thing here is going to go to 0 faster than log x goes to infinity. So this guy here is going to go to 0. If you want to prove that rigorously, just use L'Hopital's rule. But I'm not going to bother with that now to save time. So we just get the Im. So this term is just 0 minus 0, so it vanishes. So Im is just minus 1 over m plus 1 times the integral from 0 to 1 of x to the m dx. Okay, and this thing we can just integrate. So let me just write it out again here. Minus 1 over m plus 1 times the integral from 0 to 1 of x to the m dx. But this is, of course, 1 over m plus 1 minus 1 over m plus 1 times 1 over m plus 1 times x to the n plus 1 from 1 to 0. Okay, when we plug in 1 we get 1 over n plus 1, when we plug in 0 we get 0. So all in all this is just minus 1 over m plus 1 squared. So in fact we don't actually need to derive a recurrence relation. The log x, when we differentiate that, we get ourselves a polynomial, which is nice to integrate. So Im is equal to minus 1 over m plus 1 squared. And remember Im is just this integral here, which is what we have here, but in the case where m equals to n. So this integral now becomes, I can just get rid of it and replace it with, well this thing here, but when m is 2n, so that's minus 1 all over 2n plus 1 squared. Okay, and of course this minus here cancels with that minus there. So we're left with that the probability that y lies between 0 and 1 is 4 over pi squared times this summation here. Let me clean up the whiteboard and we'll continue. I know this is getting quite a long video, but I promise you it's going to be worth it. We're almost there. Okay, so we've just shown that the probability y lies between 0 and 1 is 4 over pi squared times this infinite sum here. But if we just look at this, this is 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. So the sums of the reciprocals of the positive odd integers squared. But we want to know the sum of the reciprocals of all of the integers squared. So we want to know this thing here. So s, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared and so on. Okay. Well, what I'm going to do is just split this into its odd terms and even terms. Okay, because this thing converges, which we know, which we can check by the integral test. This thing here converges and they're all non-negative terms, so I can rearrange the terms and that's perfectly fine. So I'm going to write this thing here as SE plus SO. So SE just means even terms, so 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared and so on. And the SO is just the sum of the odd terms, so 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared and so on. So this guy here, this infinite sum here, is just SO. Okay, but we want to write SO in terms of S. Well, let's firstly work out what SE is in terms of S. Well, SE is just the sum of the even terms, so 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared plus 1 over 8 squared and so on. But notice that obviously each of these terms here are even, which means on the bottom I can take out a factor of 2 squared from each of these terms. So let's do that. Let's take out a factor of 2 squared. So what I'm left with is 1 over 1 squared, because of course 1 times 2 is 2, so 1 squared times 2 squared is 2 squared. Then plus 1 over 2 squared, because 2 times 2 is 4, and 2, so that means 2 squared times 2 squared is 4 squared. Plus 1 over 3 squared, again 3 times 2 is 6, so 3 squared times 2 squared is the 6 squared there. Plus 1 over 4 squared, and so on. So we get the SE, so the sum of the even terms is 1 over 2 squared times this guy here. But if we just look at this guy here, it's precisely what S is. So SE is equal to 1 over 2 squared times S. So let me just replace this thing here with S. And of course 1 over 2 squared is just a quarter. So SE is equal to a quarter S. But we know that S is just equal to SE plus SO. So this implies that S is equal to SE, which is a quarter S, plus SO. Okay, but then just rearranging this tells us that SO is equal to 3/4 of S. Okay, so the sum of the reciprocals of the odd positive integers squared is equal to 3/4 times the sum of the reciprocals of all the positive integers squared. Next thing I want to do is just plug this thing here into this equation here, and we'll have the last whiteboard and we can get our solution. Okay, so we just showed that S0 is equal to 3/4 S, where S is the thing we're trying to work out, the Basel problem. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so on. Let's just plug that back into here. So we get that the probability that y lies between 0 and 1 is just equal to 4 over pi squared times S0, which is just 3/4 S. So this thing here is 3/4 S, and of course the 4 and 4 cancel, so we're just left with 3S over pi squared. So we've got S now, and we've got a pi squared and 3 and stuff, and it's in terms of the probability that y is between 0 and 1. So if we can simplify this thing here, we'll almost be done. And if anything, if we know what S equals, we kind of know what this thing equals, which perhaps gives us motivation or something to see, but it's not too difficult. If we just recall what y is equal to x1 over x2. And now remember, x1 and x2 have the exact same distribution. Okay, so it's not, there's no reason why one should be bigger than the other, And similarly, so there's no reason why x1 should be bigger than x2, and there's no reason why x2 should be bigger than x1, because they're distributed the exact same. So it's kind of like if I have a blue die and a red die, and they're both fair and they're both normal, and I'd roll them, there's no reason why the red one should be bigger. It should roll a bigger number than the blue one, and vice versa. There's no reason why the blue number should roll a bigger number than the red number. So when I look at their ratios, the probability that one is bigger than the other is exactly equal to the probability. So the probability that the red die divided by the blue die is bigger than 1. In other words, the probability that the red die gives me a score bigger than the blue die is going to be equal to the probability that the blue die gives me a score bigger than the red die. Okay, so we're going to apply that sort of same logic here. The probability that x1 is bigger than x2 is going to be exactly the same as the probability that x2 is bigger than x1. But obviously that if x1 is bigger than x2, then that's precisely saying that y lies between if x2 is bigger than x1, then that's precisely saying that y lies between 0 and 1. And conversely, if x1 is bigger than x2, then that's saying that y is bigger than 1. Okay, so all in all, what I'm trying to say, and I'm waffling a bit now, is that this thing here, the probability that y lies between 0 and 1 is half, kind of by symmetry, because there's no reason it would favour x1 over x2, and there's no reason why x2 would be favoured over x1. Okay, so this guy here just equals a half. Was my long and convoluted way of saying this. This equals a half, so we have that a half is equal to 3s over pi squared, and rearranging this gives us that s is equal to pi squared over 6. And that is a solution which you may have seen before. That is the answer you may have seen before, and I doubt you've seen the solution for this before. I hadn't, at least. This is absolutely insane that we can evaluate an infinite sum using probability theory, using integration, using some summation, some cheeky Fubini theorems and stuff like that. But s equals pi squared over 6, and that is one of the amazing ways you can solve the Basel problem. Thank you so much for watching. If you have enjoyed this video, please do give it a like. I'm not really sure if you enjoyed this, because I really enjoyed this, but it was kind of a long video and it's not something I usually do, but I really enjoy non-standard proofs. So leave me a like if you really enjoyed this, and I'll know to make more fun non-standard proofs and stuff like this. Crazy stuff which I hadn't even seen before. Okay, anyway, thanks for watching. I'll catch you in the next one. Have a great day.